theory class and recording myself. I'm sorry. Now, this is our empirical formula. Our last step is figure out the molecular formula. Now, we know our molar mass, so we can figure out what whole number to multiply our empirical formula by. So the first thing we need to figure out is, what's the mass of our empirical formula? If it equals to our molar mass that was given, it is the molecular formula. So we have 3 carbons plus 8 hydrogens plus 2 oxygens. And that comes out to 76.67. So that is not the given molar mass. The given molar mass is clearly going to be a bigger number because your molecular formula is either equal to your empirical formula or a bigger ratio. So our actual molecular formula is 380.47. So we can figure out what that number must be by just dividing 380.47 by our empirical formula mass. That will give us a whole number if you've done everything correctly. If you've done everything correctly, you'll get a whole number, or really close to a whole number. So this is 5. So that's our multiplier to get our molecular formula. So 5 times our empirical formula C15 H40 and our O10. You can check that because if you get the molar mass of C15 H40 O10, it should be 380.47. Yes, carbon can have 40 hydrogens because we have 15 carbons. It's a big molecule. A couple of students sadly walked into my organic review and heard all about carbon-containing molecules. And I'm sure you knew everything I was talking about. That's also organic too. So, you learn a lot in organic one. I know this one's a long work, and it's faster if you're not explaining it, but you need to understand how to do it. Because this is something that is done all the time to figure out an unknown compound. Okay, let's go through the second quiz, which is quiz 6. Oh, sorry. Quiz 5. Which of the following is not a strong electrolyte? E. Why is E not a strong electrolyte? E is an organic compound, and therefore it's not forming ions when it dissolves. It dissolves as a molecule. For something to be an electrolyte, it needs to strongly ionize, meaning forming ions. So all of these are soluble to form ions. If something is insoluble, it's not going to be a strong electrolyte. Or partially soluble, it's not going to be a strong electrolyte. So a weak acid, not a strong electrolyte. Weak electrolyte, because it doesn't completely ionize. So strong acids and water-soluble compounds are electrolytes. But organic compounds will not typically form your electrolytes because they do not dissolve as ions, they dissolve as a whole molecule. As far as how many compounds are soluble, or slightly soluble, CuOH2 is insoluble. because OH is typically insoluble with the exception of things like potassium, those group 1 and 2 metals. KNO3, that one is soluble because again, that potassium, you see that potassium, that thing is soluble. Ag2SO4, that's one of the things that is not soluble. And you do need to know your solubility rules. And K2S is soluble. Again, you see that potassium. You have that solubility. So the answer is 2. Go through your solubility rules, know them. Your net ionic equation of an acid and a base that forms a soluble compound is going to be H plus OH minus gives you H2O. That's always your net ionic equation for a acid-base reaction. Assuming that your salt is soluble, and most of the time it is. Yeah, that's really all I have to say about that. Our net ionic equation for this reaction. So we have MgSO3 that is going to form Mg plus 2 ions plus SO3 2 minus plus H and then I minus, and then we're going to switch them. So Mg and I plus our H and SO3 2. So when we switch that, we get Mg I2, and that is going to be soluble. So just redraw it as the ions because it is soluble. Plus our H2SO3, sorry, I don't know where I got that 4 from. So first off, magnesium is on both sides and iodine is on both sides. So this is, or should form, SO3 2 minus plus H plus to form H2SO3. However, as soon as you see H2SO3, you have to recognize that that's going to decompose to H2O liquid plus SO2 gas. So the actual net ionic equation is SO3 2 minus plus H plus forms H2O liquid plus SO2 gas. I did give some credit for A, because you were getting there, but you have to recognize that that's going to be a gas forming reaction. And when this forms a gas, we call this a gas forming reaction. Okay, here is our reducing agent. Okay, a nice little hint. If we have a polyatomic ion, notice it's a polyatomic ion on both sides of the equation. It forms an ion, but nothing's changing with the amount of chlorines or oxygens and how they're bond. So you can follow the oxidation numbers, but they won't change. So you don't really even have to waste your time. The polyatomic ion is not breaking up its covalent bonds. So it retains being a polyatomic ion on both sides. So you can follow the oxidation states. You're more than welcome to, but they won't change between chlorine on both sides and oxygen on both sides. So that just gives you a little bit less work you have to do. So notice how the polyatomic ion is still forming, or still retaining its molecular bonds. It's still the same polyatomic ion on both sides. Cl O4 minus 2, it's not changing. I mean, yeah, plus 2, it's not changing on both sides. So nickel solid is a free element. It has a 0 oxidation state. Silver solid is a free element. It has a zero oxidation state. Super easy. So what we see is we have that ClO4 minus 1. So, silver has that plus 1 oxidation state. Then nickel, we have 2 ClO4 minus 1s. So that means overall we have to balance that minus 2. So it has a plus 2 oxidation state. Again, you can look at the chlorine. Its oxidation state is not changing. You can look at the oxygen. Its oxidation state is not changing because polyatomic ion is retained. It's still the same polyatomic ion. No reaction is occurring to that. So now we just have to look at what's going on. So nickel, and sometimes I find it easier to break it up this way. Nickel is going from an oxidation state of 0 to plus 2. So this is an increase in oxidation state. So this is oxidation. Silver is going from an oxidation state of plus 1 to 0. This is a reduction in oxidation state. So it is undergoing reduction. Now that's not what the question asks. It asks which one's the reducing agent. The thing that is undergoing oxidation is causing the other thing to be reduced. So nickel is our reducing agent. It is causing silver to be reduced. So make sure you pay attention to what I'm asking for. Am I asking for what's being oxidized? Am I asking for what is the reducing agent? You have to pay attention to what I ask. But again, a nice little trick with the polyatomic ions, you can double check, prove to yourself that those oxidation states are not changing, but they're not because it's the same polyatomic ion on both sides of the equation. So if nothing changed with the ion, nothing can change with the oxidation state. The ratio of ions is different, but we didn't have any change in the actual compound. This reaction is not a dilution. This is a chemical reaction. You cannot use M1V1 equals M2V2 because this is a chemical reaction and we have ratios that we need to consider. Also, PbCl2 is precipitating out. So that's affecting the concentration of solute in the final material because PbCl2 is not in the final material. So for multiple reasons, only use M1V1 equals M2V2 for dilutions. If you are taking a solution and adding more water to it, you are diluting it. This is not a dilution. This is a chemical reaction. If a chemical reaction occurs, this is not a dilution. So we cannot use that, but we have to use what we know about our our equation. Our chemical equation is given to us, it's balanced, it even tells us lead chlorine has precipitated out. So it tells us all the things we need to know, you didn't even have to do that. What we are being told is, we want to know what volume of a 0.244 molar potassium chloride solution is required to react exactly with 50 milliliters, a 0.210 molar PbNO3 solution. So first off, what we know, ignore the solutions for now. What we know is that 2 moles of KCl are required to react with 1 mole of PbNO3 because that's what our coefficients tell us. So if we know the amount of moles of PbNO3 we have, we can calculate the amount of moles of KCl we need. Can we do that? We can, because we know our volume of our PbNO3 solution. So we have 50 milliliters of a solution of PbNO3. We put that in a flask. Of that 50 milliliters, we have some water, we have some PbNO3. That's what's in that. If I measure out 50 milliliters of this solution, I put it in a flask, I have some water, don't care about the water. And then I have a certain amount of PbNO3 molecules. The question is, how many moles of PbNO3 do we have in this solution? The only way we know that if we know our concentration. Our concentration tells us that we have a 0.210 molar PbNO32 solution. Molar means moles per liter. So what that tells us is we have 0.210 moles of PbNO32 for every 1 liter of solution. So if we took 50 milliliters and we put it in a flask, some of that's water, some of that's PbNO32. So the question is, how many moles do I have? Now again, this relationship is per liter, so we need to convert our 50 milliliters to liters. So we need that conversion. And you can do that, you can show that in the conversion. Because again, this relationship is in liters. So notice, we have a solution that's 0.210 moles, but we only, per liter, but we didn't add a whole liter. So that means we're going to have less than 0.210 moles. And you should be able to rationalize this because it makes sense. So you should be able to rationalize this. In 1 liter, I have 0.210 moles of PbNO3, but I only added 0.05 liters. So that means I don't have a full 0.210 moles. So I'm going to use my concentration to figure out how many moles of PbNO32 solution I have in my amount in my flask. So I'm going to divide by my liter solution, and that tells me that I have 0.210 moles for every liter. So if I figured out that number, I don't need to, but if I did, that would give me my moles PbNO3 that I actually have. And then I know, based on my equation, that I need 1 mole of PbNO3 to react with 2 moles of KCl. So this tells me how many moles of KCl I need to react completely with the amount of PbNO3 I have. And I can figure out that number if I wanted to. I don't need to because that's not what the question's asking, but I could. Everyone's following me up until this point? Our last step is we want to know how much, we know our moles, but now we have a solution of KCl. And we are told the concentration of that solution of KCl, which is for every 0.244 moles of KCl, I have 1 liter solution. I know how many moles I need, so now I can use that concentration relationship to convert how much liters of KCl solution I need to mix with my other reagent. So remember, your molarity is your relationship. So I want my moles KCl on the bottom so they can cancel out, and that gives me my liter solution. So when I figure this out, this will give me my answer in liters. So I want it in milliliters because that's what it's asking. You can do this separately after. But when I figure that out, it's 86.1 milliliters of my KCl solution. That will give me enough moles to completely react with the 50 milliliters I took out of my PbNO32 solution. So when you have a molarity solution, you typically want to convert it to figure out how many moles you're actually adding. So you have a volume and you have your molarity, you can figure that out. Now this one is a dilution. We want to know the concentration of a solution prepared if we take 25 milliliters of a solution, a 0.188 molar solution of whatever that is. It doesn't matter. It really doesn't matter what it is. And then we add, or we diluted it to a total of 150 milliliters. So that means we added 125 milliliters of water. So how much is my concentration now? Well, clearly my concentration has to be lower than 0.188 molar because I just added a bunch of water to it. So the amount of solute didn't change. So I just added a bunch of water, it's clearly going to be more dilute. So B, not the answer. Don't know anything else so far, but I know B, not the answer. So you can use some rationalization to do that. So M1 V1 is equal to M2 V2. And it doesn't matter which measurement your volume is in, as long as V1 and V2 are in the same, because it'll cancel out. It's just a ratio. You can convert them to liters, it won't change your answer. You can play around with that. So M2 is equal to 0.313 molar. Notice the difference between 6 and 7. 6, we had a chemical reaction. 7, we didn't. It's just a dilution. Last one. We want the percent yield. We're told 28.16 grams of CO2 is formed. First off, this is our actual yield. We do not need this till the very end. This is what's formed, this is what we collected. We do not care about this until we actually figure out our percent yield. And our percent yield is actual yield divided by theoretical times 100. So what we need to know is this. We're given our actual, so ignore it for now. So we are told we took 4 moles of C8H18 and 4 moles, I left off an oxygen, of O2. And we want to know what's our theoretical yield of CO2. So we need to calculate our possible yield using both of those reagents. So first off, let's calculate yield using reagent 1, C8H18. So we know we reacted 4 moles of C8H18. And we want to know how much CO2 is going to form. According to our reaction, it takes 2 moles of C8H18 to form 16 moles of CO2. Now I know this isn't the lowest whole number ratio, but that's irrelevant. You can really use 1 to 8, but you don't need to. And it's going to come out the same. Notice the relationship from my reaction is in moles, and I gave you moles. So you do not have to convert this to grams. There's no reason. Unless if I asked you how many grams of C8H18 you started with. It's the only reason. But it's already in moles. Don't give yourself more work. So our 2 moles of C8H18 goes on the bottom, so it cancels out. And our 16 moles of CO2. Now that coefficient, 16, is for CO2. Don't switch that up. Keep that with CO2. I'm going to eventually need this in grams. You could just convert this to moles and see which one's less, but it doesn't really matter. I'm going to eventually need one of my yields in grams so I can figure out my percent. So my molar mass of CO2 is 44.01. So that could totally produce 1,408.32 grams of CO2. That's a possibility. But I need to see if I have a limiting reagent. So I have to do the same thing with O2. It's going to look very similar, but we don't have the same ratio. So we're going to calculate the yield from O2. Again, we're starting with 4 moles. Now here, according to my equation, 25 moles of O2 is needed to react with 16 to form 16 moles of CO2. So I have a different relationship between one reagent and my product and my other reagent and my product. And again, that's based on my coefficients. So my 25 moles O2 go on the bottom, and my 16 moles CO2 go on the top. Now again, I'm going to convert that to grams so I can compare the two and see which one is limiting. I cannot calculate my percent yield until I do this. So that only forms 112.67 grams of CO2. So this is limiting. Our CO2 is limiting for this example, for the amount of moles I use. And this is my theoretical yield in grams. So when I figure out my percent yield, this is what I am going to use. I already have my actual. It was given. That's what was actually formed. So my percent yield is going to be my actual, which was given in the equation, 28.16 grams CO2. And my theoretical is what I just calculated. That comes out to 25%. Now note, if I tell you one of the reagents is in excess, that one's not limiting. Because that's what excess means, that there's some left over. So if I tell you that, don't try to calculate the two to compare, because the one in excess is always going to be not limiting. So just make sure you read your equation. Technically your theoretical yield can be in moles, but since our actual yield was given to us in grams, we needed to use grams for the percent. Any questions? That was quiz 5. Now let's go over the latest quiz. No. I did that thing where I just replaced quiz 6 with quiz 5. So now I gotta go get it from my computer. Before we go through that, since I gotta go all the way and get it from my computer, bless you, I'm gonna go through I put up two examples that were not on the quizzes because we went over it in class. So I'll go through those two. That's just two examples from what we went over that wasn't part of the quizzes. But it's still relevant. It's still what we went through in class, so we could go through it. So this is a gas equation. We're told a 0.465 gram sample of an unknown compound occupies a volume of 245 milliliters at 298 degrees Kelvin and 0.122 atm. And we want to know the molar mass. Remember, molar mass is equal to your mass in grams divided by moles. Guess what? We have the mass. So all we need to do is find N. And we can find N because we have V, T, and P. So PV equals N or T, and we have PV and T. So we can find N. N is equal to PV divided by RT. Now one note, volume is in milliliters, so we have to convert that to liters. So that is one thing we do have to do. Temperatures in Kelvin, we're good there. Pressures in ATM, we're good. So we can convert our amount of moles We already have the mass. So pressure, 1.22 atm, times our volume in liters, divided by R, times our temperature in Kelvin. So that leaves us with our moles, and that is 0.01222 moles. And again, I'm keeping a bunch more numbers than I need because of rounding issues. So to figure out my molar mass, I know the amount of moles that I have. I know my mass, so I can figure it out. Because it's just grams divided by moles. So that is just 38 grams per mole. And I could figure out a compound on the periodic table that it might be close to. And the second example, before I go get those other ones, this is another one, but this is a partial pressure and total pressure problem. So we want to know the total pressure. I'm just going to put T. If a flask has a volume of 6.00 liters, we're assuming that the gas can't escape. That's kind of important. We know the amount of moles of one gas, H2. And we know amount of moles of our other gas, which is N2, which is really irrelevant which gases it is because we're given our moles. And then we know our temperature, which is 20.0 degrees Celsius. As soon as you see a temperature anywhere in this chapter, just convert it to Kelvin. That's true for Charles' law as well. Because that's what you needed in. So I just do that right away. So we want to know our total pressure. Remember, still PV equals nRT, but P total is going to be required that we know N total. We know our individual N's, so we can figure out N total. N total is going to be equal to NH2 plus our moles of N2. We have those, so we can calculate them. So our N total, our total moles, is going to be 0.415. Once we know our total moles, now we can calculate our total pressure. We have volume, temperature, we have R, we have our N total. Remember, your temperature has to be in Kelvin. And our volume is already in liters, so we didn't have to do any conversions. So our P total, when we calculate that, is 1.66 atm. I could also figure out my partial pressure of H2 and my partial pressure of N2, because remember, your volume and your temperature is not changing. Okay, let me go. I don't know why when it saves it, it gets all bubbly. It's so weird. Okay, let's go through this last quiz. Volume of a gas is proportional to the temperature. Which law is that? Charles. Boyle is our pressure and volume. And Avogadro's has to do with our moles. So that's what you're looking at. And your ideal gas law is everything. Which of the following samples will have the greatest volume as STP? They all have the same because the gas takes up the container. So that's at 22.4 liters. They all have the same moles. They all have the same volume. Okay, so here, what volume in milliliters? Well, a sample of some gas, it doesn't matter. Occupying a syringe, this is Boyle's law. At 5.5 atm, if the gas has a volume of 25.0 milliliters at 1.2 atm. So this is our P1V1 equals P2V2. What that says is, the more pressure, the smaller the volume. So we already know that we should have a smaller amount of milliliters than 25 as our final product, just based on what we know about that relationship. Though all of these, well, B is clearly a bigger volume, so you should recognize B is not the answer. All the other ones we have to do the actual calculations. So P1 is 1.2 atm, V1 is 25 milliliters. Then we applied some pressure, so that's P2 is 5.5 atm. We want to know V2. V2 is going to come out in milliliters because that's what V1 is. As long as P1 and P2 are in the same units, we're good. So P1 times V1 is equal to P2 V2. So solving for V2, our answer is 5.5 milliliters. ATM cancels out, we're left with milliliters. Any problems with that one? Okay, the next one is actually Charles' law. We're looking at what volume a sample of gas will contract. Hey, it already told you the volume is less. Told you that in the example. It said contract. We know contract means less. If it is cooled from 500 degrees Celsius to 50 degrees Celsius. And we knew its original liters. So our T1 is going to be 500 degrees Celsius, and our V1 is 5.58 liters. Our T2 is 50, and our V2, we don't know. As soon as you see Celsius, add 273.15. Because this has to be in Kelvin, because we don't want a T equals 0. Volume could be in liters, that's fine. So our relationship is V1 divided by T1 is equal to V2 divided by T2. So we originally had a temperature of 773.15 degrees Kelvin, and we originally had a volume of 5.58 liters. We don't know our V2. Sorry. You can multiply both sides by 323.15 Kelvin. Our kelvins cancel out. Our V2 is equal to 2.33 liters. Which makes sense, it should be smaller because we compressed. And it told us that we were contracting. So we really could have left out C, D, and E because it told us the volume was going to be less. So using some common sense for these will help you from making a simple mistake. Think about what's happening. Here is another PV equals nRT1. This one's fairly straightforward, except we want the mass of NO2. We know the volume of a tank. We know the pressure of the tank. And we know the temperature. Now we can't directly calculate the mass, but we can calculate the moles. And once we have the moles, we know the NO2's molar mass, so we can calculate the mass. So just because it's asking for mass, don't let it trip you up. So we can calculate our moles. Moles is going to be equal to PV divided by RT. I'm just solving for N. Pressure is an ATM. We do not have to do a conversion. Volume is in liters. We do not have to do a conversion. Or is always or. And then temperature is 385 Kelvin. Fairly straightforward. So this gives us our moles. The nice thing about chapter 5 is we're basically doing the same thing over and over again. So it's kind of a lot of memory there. Now once we have our moles, we can calculate our mass. We've been doing that since a bit ago in this class. Our molar mass of NO2 we can calculate from the periodic table because we have 1 nitrogen and 2 oxygens. So that's 46.01 grams of NO2 is equal to 1 mole of NO2. So that gives us our mass at 86.7. So don't let it trip you up because I'm asking for mass. If you know moles, you can figure out mass. What volume will 0.780 moles of helium occupy at standard temperature pressure? There's 2 ways you can actually figure this out and you'll get the answer of D both ways. One is just using the fact that 1 mole at standard temperature pressure is equal to 22.4 liters at STP. So we're given our moles. And we have this relationship because this is at standard temperature pressure. That gives us 17.5 liters. If you didn't remember this number, and it was given to you on your sheet, but if you didn't remember this number, because it won't be given to you tomorrow, you can calculate this using PV equals nRT, because again, volume is just equal to nRT over P. And you know pressure at standard temperature pressure, it's 1. You know temperature, it's 273.15. So therefore, you know the moles, you can calculate volume. And that will also give you 17.5. And they both work. They're both correct ways to work it. So as long as you know that standard temperature pressure is pressure 1 atm and temperature 273.15 Kelvin, you can figure this out. So you don't necessarily need this relationship, but that's a little bit easier of writing. They both work. Check both ways. The last one, we want to know what a gas is if we know the density. So we know that, oh, and I'm sorry, this should be per liter. So we know the density. We want to know our gas. But we know density at STP is equal to molar mass divided by 22.4 liters. So we have density. We can figure out molar mass. So that means 1.78 is equal to molar mass divided by 22.4. Our molar mass is equal to 39.87 grams per mole. And argon is 39.95, so that's really the closest. Neon is 20.18. NO2 is 46.01. That's just my molar mass. O2 is 32, and Cl2 chlorine gas. Remember, chlorine gas, oxygen gas, bromine, all of our halogens, they're all diatomic. So if I tell you chlorine gas, you need to know the molar mass is not 35 point whatever, it is Cl2, so it's 70.9. But pretty straightforward. So of course argon is the unknown gas. Now remember, if you're not using it as standard temperature pressure, then your density is equal to P times molar mass over RT. So again, you know pressure is 1 atm, you know temperature is 273.15. At standard temperature pressure, you will still get your molar mass to be the same thing. So you can use either of these because you do know what those are. Any questions? Hey, y'all have a good night. If y'all have any questions, let me know. If you try to email me tonight, I can try, but it's unlikely I'll get back to you because I'm not going to get back to New Orleans until like 9:30. So, you know. But we went through this pretty quickly. I'm sorry if I was talking really fast. I just, you know, wanted to be done.
So, is it okay?